Hello, everyone. Hello, and welcome to the 2025 Math Kangaroo live solve. We're so glad to have you all here. So, before we jump into the amazing math problems that we're going to be going over today, we have actually a Math Kangaroo representative here with us. So, first, I'll introduce this amazing representative. We have with us Timothy, who is currently a high school senior and is a Math Kangaroo gold medalist, teaching assistant, and instructor. And he was recently named an Ellison Scholar, which is one of only 20 students selected worldwide to receive full support to study at Oxford University this September, which is really impressive.
Yeah, and I'll just say a little bit more about Timothy. So, Timothy is a passionate mathematician and computer scientist interested in pushing the boundaries of computational problem solving. In 2024, he co authored research papers on machine learning augmented astrodynamics and prediction of neo-antigens, published at Massachusetts Institute of Technology Undergraduate Research Technology Conference. He loves teaching younger students mathematics and has worked as a math teacher at School Plus and Math Kangaroo, helping prepare students for competitions and fostering a passion for problem solving. Outside of academics, Timothy is an avid board game enthusiast and a dedicated athlete in fencing. He is planning to study at Oxford, majoring in mathematics and computer science as an incoming Ellison Scholar. So everyone, please welcome Timothy.
So I've always loved math, and my parents would always give me math workbooks to work on. Every time I'd go pretty much anywhere, I'd have a math workbook on my lap, and I would pretty much do them before I could even talk, before I could form a full sentence. My first experience with Olympiad math was when I started taking Math Kangaroo, and that was back in kindergarten when they let me take the levels 1 to 2 test. Ever since then, me and my brothers have always made sure to take the test each year. And when I even got to high school, I was offered the privilege to be a teacher assistant at Math Kangaroo. So, one of the main things that I learned there is that it's one thing to know and be able to solve mathematics, but it's another to be able to teach it. And you can learn a lot from not only interacting with other students, but also people that are much younger than you and to understand where their mind goes and wanders. The following year, I was also given the opportunity to go to the Math Kangaroo math camp at Zakopane, Poland, where I met a lot of smart mathematicians from all over the world. Math Kangaroo encouraged me to also apply to Ellison Scholarship, and I'm very grateful for that fact. The main takeaway from sort of my math journey, I want to say, is that you should always follow your passions. Stay open to new experiences and take every opportunity that comes your way, even if you think it's a shot in the dark, especially the ones that even might scare you a little bit. Growth doesn't come from following a set path, but from being willing to explore the unexpected. I could never predicted where my choices would lead me, but by embracing every step of the way, no matter how small, no matter how daunting, I found myself part of communities, experiences, and challenges that shaped who I am today. Because I kept saying yes, because I kept being encouraged by my motivation, I have no regrets and a lifetime of lessons, friendships, and memories. So, what I want you guys to take away is if you follow what you really love, and if it's mathematics, so be it. Get in deep into mathematics, make sure you learn a lot, and you'll definitely get a lot out of it.
Yeah, thank you so much, Timothy, for that really great advice and really inspirational words. I think now that we've heard from you, heard more about what Math Kangaroo represents, we can go into some problems. But before we get into them, we have to first introduce ourselves because you have no idea who's talking to you right now. So first, I'll introduce the person that's at my left right there, Henry Jiang, who is a Math Olympiad qualifier since 8th grade, attended the Math Olympiad program in both 2022 and 2023, and outside of math, he enjoys playing chess and learning about geometry trivia.
I enjoy everything that starts with geometry, geography, geology, all of that. So, hello everyone. I'll be one of the two people covering this live solve. At this point, you're probably wondering who the other person is. So, now I'll introduce Eli Gold, who is on my either left or right, depending how you have your screen set up. So Eli is a three-time Amy qualifier and a USA MTS perfect scorer. And percussionist, which is really cool. He's won many national and international competitions playing the marimba. And he also has many hobbies, such as, for example, tap dancing, which is really, really impressive. I never know how people are able to like get all the rhythms correct. That's so cool. So everyone say hello to Eli.
Hello, everyone. I'm excited to be here. I know Henry's excited to be here too. And I saw something in the chat that I'm famous in the world of PSL. I don't even know what that is. So I'm glad that I'm famous in it, though. That's cool. Cool. I think now it's time to get into some of the questions that we have today because that's what this is about. It's a live solve. We're going to go solve these questions, never seen them before. We're just going to try to figure them out on the spot. So I think our first question is this one right here from grades 3 and 4, question number 10. I'll just read it really quickly. Anna, Bonnie, and Charlie have some kangaroo cookies on their plates, as we see here. They then share the remaining 15 cookies on this tray so that everyone has the same number of cookies on their plates. And the question is, how many of the cookies from the tray does Anna get? Anna, the first person here. And okay, so it's a lot of cookies going on here and a lot of things that are in the shape of kangaroos, which is scary because we're dealing with math kangaroos here, and the math kangaroos seem like they're attacking us, but it's okay. We can figure this out. So I know that I want them all to have the same number. Right now, Anna has 3, Bonnie has 4, and Casper has 5, right? So I think there's like quite a few different ways we could do this, but maybe one natural thing to do would be to just like make sure they have the same number, like they all have 5 first, and then start adding more from there. So, well, how do I make sure that Anna also has 5? We can just give 2 cookies to Anna. So let's start by giving 2 to Anna here, and then give 1 to Bonnie, and then give 0 to Casper, right? And when we do that, we're sure that there's 5, 5, and 5, right? Because, well, this would be 2 plus 3, 1 plus 4, and 0 plus 5. And so then how many cookies do we have left on the tray? Well, we have 15 minus the 2 plus 1, so minus 3, which is 12. So we have 12 cookies left on the tray, and we need to fill out the rest of these 3 people and just give them all the same number, right? So we can just take this 12, divide it by 3 to give each of them the same number, and of course 12 divided by 3 is equal to 4. So we give 4 more to each of them. So we have 4 more here, 4 more here, 4 more here. So in the end, how many cookies does Anna get from the tray? Well, it's 2 plus 4, so 2 plus our 4, and that, of course, is equal to 6. So the answer, I think, would be 6, or option C, and that seems to be what I see a lot of people getting in the chat, so I can be pretty confident that it's correct, but I just got to be sure, got to be sure. So let's see. Is C the correct answer? Hey, I think it is. Awesome job, everyone in the chat, for getting that answer correct. And I think we can move on to the next question. So Henry, would you take it away?
Wow, you really solved that question really fast. You like jumped through it like a kangaroo. Let's see if we can do the same thing on our second problem. So our second problem has 5 different people who are using their phones, and we need to figure out who had each of these phones. And they tell us that Bob has spoken on the phone as much as Anne and Christina together, and Bob ran out of power. David had not used his phone at all, and we want to know which phone belonged to Edward. So first, we need to figure out what we can immediately get from this, because these are a lot of words, and I don't want to do literature. I already took my literature exam 2 years ago. So we need to figure out what each of these sentences tell us. Well, Bob ran out of power is one of the easier sentences. We can immediately put Bob here. And David did not use his phone, so we can immediately put David here. So now we need to think about what to do next. And in this situation, you should always think, what information have I not used yet? Well, we haven't used the fact that Bob has spoken as much as Anne and Christina together. Well, that means that we can take these 3 and figure out which one belongs to Anne and Christina. If number 2 was one of Anne and Christina, then the remaining person would have to also have used half their battery, which is impossible, which means that Anne and Christina have to be phones 4 and 5 in some order. We don't know what order, but luckily it doesn't matter because that leaves us with Edward on phone number 2, which, as I saw a lot of you put in chat, some of you even put the total pairing of all of the people, gives us an answer choice of B. So let's check if B is the correct answer. Drum roll, and it is. Amazing. So now we can move on to the next problem, now that we've figured out this phone conundrum.
Yeah, that was a really, really awesome solution. Thank you so much for finding that, Henry, and sharing it because I mean, I didn't even know what to do with phones 4 and 5. It seemed like there wasn't any way to figure out which one belonged to which person, but actually it doesn't even matter because we can just go to phone number 2 when we realize that phones 4 and 5 are A and C in some order. But anyway, I think now we can move on to this question here. So this is grades 7 and 8, number 8 here. There are 10 more truth tellers than liars in a room. Truth tellers always tell the truth, and liars always lie. Now, everyone in the room was asked, "Are you a truth teller?" And everyone gave an answer. A total of 20 people answered yes, and were asked, "How many liars are in the room?" Okay, this is a quite strange logic question, but here we go. So, a total of 20 people answered. I mean, I assume, yeah, everyone gave an answer. That means that there's 20 people in the room, right? And there's 10 more truth tellers than liars. So, I mean, you can kind of just isn't like, do you even need to? Oh, a total of 20 people answered yes. Okay, not a total of 20 people answered at all. Okay, I understand what's going on now. But I guess that doesn't actually matter. There are 10 more truth tellers than liars. So let's say that there's like T truth tellers and L liars. That'll maybe make things useful. Then we know that T is 10 plus L, right? So 10 more truth tellers than liars. Everyone in the room was asked, "Are you a truth teller?" Okay, I think this is where I was going with this. You know, if you're a truth teller and you're asked, "Are you a truth teller?" you'll say yes. And if you're a liar and you're asked, "Are you a truth teller?" you'll also say yes because you're a liar. And so if a total of 20 people answer yes, well, I mean, that just means there's 20 people in the room because everyone is going to answer yes all the time, right? Because if I'm a truth teller, I'll say yes, and if I'm a liar, I'll also say yes. So I know that there's a total of 20 people, which means that T plus L is equal to 20. And now if I plug in that T is 10 plus L, that means that 10 plus 2L is equal to 20. And so subtract the 10, 2L is equal to 10, which means L is equal to 5. And so that means, of course, that T is 10 plus 5 or 15. And that should check out, right? Because 15 plus 5 is 20, and there's 10 more truth tellers than liars. So I think that's leading me to option oh, wait, L is 5. Okay, this is the number of liars. So that's leading me to option B here. I'm seeing some people, like a lot of people saying 5, like option B. Some people maybe saying option D, but I think there's some agreement that B should be the answer. So let's see if we're correct. All right. Is B the right answer? Yes, it is. We got it. Okay. I think we're ready to move on to the next question. Henry, would you take us there?
Wow, that was really impressive. I guess you must really be locked in. But speaking of locks, our next problem, which is from grade 7 and 8, number 10, is about a lock. So here we have this sort of bicycle lock. If you have a bicycle, you've probably seen this type of spinny lock thing before. And the code here, which is in the row with the arrows, is 0000, but if you look at it from the side, you'll actually see 8888. So now we're looking at Paul's friend's lock, and when Paul looks at the lock, he sees 2815, and we want to know the real combination of his friend's lock. So I've noticed that what you see and what the actual code is happens to be exactly 2 off. And we need to remember that we're working on a circle. Each of these is a sort of circle thing, so it wraps around. If you see 8, the actual code would be 0 because it wraps around every 10. So let's just go through each of these and figure out what they wrap around to. If you see 2, then the actual code would be 2 more this way, so that would be 4. And if you see 8, you would get 0. If you see 1, you would go 2, 3 to get 3, and then 5, 1, 2 to get 7. So the answer should be 4037 by taking each of these and incrementing them by 2. This is actually a very interesting and common idea in math. You might have heard of it before. It's called modular arithmetic, which sounds really fancy, and I will admit it is very fun to say. And this just means you do math on a sort of circle, which is actually surprisingly useful for a lot of different things. So now the next time you see a bike lock, you can say you're doing modular arithmetic. But let's see if we got our answer correct. And indeed, the answer is A, 4037. Great job to everyone who put their answers in the chat. And I think that means we can move on to the next one. Oh no, Eli, it seems that Rat Chile has gone and eaten your microphone.
Well, I think I got my microphone back, so no worries. I was locked in a cage actually. Rat Chile had locked me up before and turned off my microphone, but it's okay. I escaped the cage. Now I'm locked in again, and I'm ready to figure out grades 5 and 6, question number 4 of this Math Kangaroo live solve. Okay, a cube is decorated by gluing identical gray squares on it. All the faces of the cube look the same. How many gray squares are there in total? That's interesting. So we're just taking these squares, and some of them look normal, like we're just gluing them onto the face like this, and some of them are going over a crease, and they look kind of weird like that. But, I mean, it seems like there's some symmetry here, so I think we should be able to figure it out, even though there are these weird square-looking bent things. All we want to know is how many squares we glued onto them. And if we see that every time we're over a crease, we really just have like half a square, you can imagine that this is 1/2 of the square and this is another half of the square, then I think all you have to do is look at like a single face of this, right? I look at just this one face. How many squares are in this one face? Well, there's the one middle square. There's this full square, right? Because it's half and half. So there's that one. And then there's this half one over here, which gives us 3 in total. And we don't have to worry that we're like overcounting or anything, because remember, this is like half a square, and it's going to be, the other half of it is going to be counted on this one. So all we have to do is take this 3 squares per face and multiply by the number of faces. And how many faces are on a cube? Well, I mean, that's pretty well known. It's 6 faces, but if you don't believe me, you can imagine like this face has an opposite face over here. Oh, it's kind of like over here, you know what I mean? And then this top face has an opposite face over here, and this side face has an opposite face over here. So that would be 6 in total, like 2 for each of these, right? Because each of these has an opposite face. So that would be 3 times 6, which I believe gives 18. And that looks like option B to me, as a lot of people are saying in here. Yeah, as Sharon is saying, this is like a mirror, all these different faces that we have. And so I believe B, or 18, should be our answer, but I don't know. Maybe I've made a mistake. I don't think I have. You know, I'm no square. I'm unique and original. I don't know. Like the hippies called people squares if they were boring. Well, I'm not boring because I got the right answer. So there you go. I think I can send it back to Henry.
Woo. All this fast math has got me really hungry. I could really go for a pizza right about now. Luckily, I know a guy who makes really good pizzas. So there's this guy called Max who, I don't know, maybe he'll do a live solve at some point. But Max right now is busy making a delicious pizza with 5 different types of toppings. There's tomato slices, black olives, chilies, mushrooms, and onion rings. Delicious. I don't know why the stem is still on the chilies, but I won't complain. Maybe it adds flavor. But we need to figure out in what order the toppings were put, particularly what was the third topping put on the pizza. Hmm, how would I even do that? I didn't watch him make the pizza. But they gave us a nice picture of the pizza here, which means we can actually see what's on top of what. And since, for example, the tomatoes are under the mushrooms, there's no way that he put the mushrooms on first. So that means we can actually make a ranking of the order that he put the toppings on. So I'll just start making this ranking from first to last. And I'll use the first letter of each of these toppings. So for tomato slices, I'll write T. So let's see what's on here. Well, I see a mushroom on top of a tomato slice, so I can write M and T. Notice that I'm writing them far apart on purpose in case there's something in between. And then, let's see, the chili is on top of the mushroom, so that's there. And then the mushroom is on top of a black olive, which means that we can put the B here. Whoa, we've already got 4 of the 5 things placed. We just need to figure out where the onion rings go. Well, here there's an onion ring under a black olive and above a piece of tomato. So that means that the onion ring must go between the olive and the tomato. And now you get to see that I actually didn't leave enough space. But that does tell us that the third thing would be the black olives. And I see that a lot of you in chat are putting the entire ranking in as well, which is very impressive. So the third thing that Max put on my delicious pizza should be the black olives, which are white on the screen, but don't worry about it. So let's see if our answer is correct. And indeed it is. That means I didn't make any mistakes, which means I can go enjoy this delicious pizza. And we can move on to the next amazing problem.
Absolutely. And you know, all of this discussion of pizza has made me hungry, and my favorite shape of pizza is actually not a circle like you saw there, but it's a square. And so I want to talk about squares, and that's what this question's about. Bob makes a square from 4 rectangular pieces. 3 of the pieces are shown here, and our question is, what can the 4th piece possibly be of these options here? And so, well, if we look through them, I think one natural thing to do maybe is just to say, well, first of all, we have a perfect square, right? And it's made of a bunch of smaller squares. So there have to be a perfect square number of pieces. So maybe first, I don't know if this will get us to the answer, but maybe it could just narrow it down. We could see how many squares we actually need to add to get a perfect square. So let's count this up. Like this is 2 by 4. So this would be 8 squares from this. This is 5 by 2. So there's 10 squares from this. And this is 6 by 1, so there's 6 from that. If we add these together, it's 6 plus 8, which is 14, plus 10 gives us 24. Okay, so, I mean, plus 1 would be 25, and I'd have a 5 by 5 square. That would be fine, but none of my answer choices are a singular square, so it's probably not that. The next square that I have is 36, right? And so if I go from 36 to 24, that's a difference of 12. So if I have something that has size 12, I know that it could possibly work. So let's go through our options here. A is 3 by 5, so that would be 15. I don't think that works. B is 1 by 5. That's definitely too few. C is 2 by 3. That would be 6. That definitely doesn't work either. D is 2 by 6, and E is 3 by 4. Both of those could work, right? Because, again, those are both 12. So I think we have to investigate both of these options, but it's good that we at least narrowed it down. So I'm just trying to imagine what this type of square could possibly look like, right? Well, if it's 36, which both of these options would tell us that it should be, then we need to have it be 6 by 6, right? And I see that this is already 6 across, which means that if I use this in my square, this has got to be like one of the sides. It can't be, well, I guess it could be somewhere inside, but it can't be jumping off of something else. Like it can't be this attached to this part over here, like going over here. It'd have to be underneath it. You know what I mean? So I think that means that this is going to be like on the bottom somewhere because there's all this other stuff that's going to happen in between. So I see that this is a 5 by 2. And so it would make sense if this was on the bottom to make this a 6 by something. So I'm imagining this is like over here. Maybe it's 6 across this way, and then this would be 6 across this way. And then this is a 4. So maybe that could jump on top of there or something. I don't know. I'm trying to see how this could work, and use either of these options. Since this is a 6 by 2, this could also be put on top of this somehow. Yeah, this is strange. Oh, well, no, I'm thinking I see how this is going to work now. Because this is a 4 by 2. I was just trying to see how I could use D here, but I actually think D doesn't work. I think I have to use E. If I make this be, because this is a 2 by 5, if I put this below this one over here, this 2 and this 4 would make 6. Okay, so now I'm starting to see how this works. Maybe if I have some larger things here, I can make a better picture. So I'll start with my 4 by 2, and I'm going to add my 2 by 2 to the bottom of it like this. Well, not 2 by 2, but 2 by 5, and then I'll add the rest of this over here. So this will be like this. So that's this piece that I just added here. So that's this piece. I moved it down here. And now that leaves enough room for this piece, right? Because that's a 3 by 4, which is perfect for this piece here. I could add that right here and add in all the lines, like we do. There we go. That fills out this grid. And then we have just enough room for this piece here. Took some time, but I got there. And there we go. We have our perfect 6 by 6 nice grid. I think that works. So if we go back to our answer choices, I believe that would mean E is our correct answer. It's hard to visualize this, I must say, because there's all these different ways that these pieces could line up, but I just realized that you could move this one down here, and that leaves a perfect little spot for part E here. I don't know if D could be used. Maybe there's a way of showing that it can't be. I don't quite see exactly how you would go about doing that, but I know at least that E does work, and we narrowed it down to D and E, so I'm pretty sure the answer is E. Let's go see if we're correct here. Looks like we are. Fantastic. Okay. I'm kind of tired of squares. Hopefully Henry doesn't have yet another square problem for us, does he?
Well, let's see. It does appear that I do have another darn square, but maybe I can think of something fun to do with this square, like cut it into a snowflake. So let's see. I took this piece of paper, I folded it in half and then in half again, and then I cut it in some sort of pattern and then unfolded it to make this snowflake. Or actually, I lied. I didn't do that. It was Nella's doing. I just accidentally took her credit. Sorry about that. But either way, we can make fun patterns by cutting paper and then unfolding it. But we want to know what the original cut was. Well, this pattern looks very, very complicated. Maybe there's some easy thing we can get from it. I just noticed that this pattern is not showing up very well, so I'll actually outline it. We have a strange thing with these diamonds in the center. Woo. And I see that a lot of you are already getting the answer. How could you get the answer so quickly? Well, maybe one thing we could try is to try it with some easier pattern and see what happens. So let's say maybe we cut a piece of paper just here or something. And then if we make that cut, we can unfold it. So there would be another cut here. And then if we unfold it again, that's a horrible square, but you get the idea. There's another cut there and another cut there. So there's 4 copies. So maybe this can be written as 4 copies of something. So let's divide it vertically and horizontally. And it appears that in each corner, you have a sort of X shape. So it would be really convenient if that X shape was actually one of our answer choices. But as a lot of you have noticed, answer choice number B is in fact that X shape. So that should be our answer. Of course, we should check that it is the right answer. And in fact, it is. Wow. So now we can all go and make epic snowflakes just by cutting an X shape and then unfolding it.
You know what has to do with both squares and snowflakes? Calendars, because winter is on the calendar and calendars have squares in them. I guess these are rectangles, but whatever. Okay, the picture shows the page for 1 month of a calendar without any of the dates listed. The total of the dates for the 2 shaded days right here is 29. On what day of the week does the first day of the month fall? This is an interesting question. I think by total of the dates, it means like the day number and the day number like added together. So it's like 2 numbers added together to 29. And this shouldn't be that bad because we can actually just count the days in between the 2 shaded days, right? Which, takes some counting, but it's not that bad if you think like just going from Thursday to Thursday is plus 7, right? So this would be, if this is x plus 7, and this is x plus 14, and it's like going back one, so it's kind of x plus 13. So I'll call this x, then this thing over here is x plus 13, which is kind of hard to see, but it's okay. So that means we have x plus 13 is equal to 29, or 2x, and then I'll subtract the 13. 29 minus 13 is, let's see, 26, 16, I think. So that would mean that x is 8. I think that sounds good. So that would mean that this day is the 8th. And now I can go back 1 week, and that would mean that Thursday is actually the 1st, right? Because then it would be 1st, 8th, 15th, then 22nd, minus 1 is 21st, plus the 8 would be 29. Hey, it all works out. So I think that means that Thursday would be the 1st of the month, and that looks like option D to me. I see Albert saying Thursday, Monil saying D, Albert saying D, C saying D, which is kind of funny because the name is C, but okay. Looks like, C, you've betrayed your letter and you've gone with D, but I think you might be right to do so. So let's see. Let's see if D is the right answer. It seems like it is. Great job, everyone who got that right. Back to Henry.
Wow, so that was amazing. And while Eli was doing that fun calendar problem, I was actually busy making a snowflake. So I'm starting to really like these pretty patterns. So I hope I get a problem that has some pretty patterns in it. Ooh, it's a hexagon, and there's a bunch of triangles in it. And I need to know what fraction of the hexagon is shaded. Well, that's a lot of triangles. It would be really convenient if there was some nice property, like maybe all the triangles have the same area or something like that. Well, let's see. I remember from geometry that 2 triangles have the same area if they have the same base and height. And we also know that this is a regular hexagon, which means that we have a lot of nice symmetry. So like I could flip it this way and it would be the same thing, or I could flip it this way and it would be the same thing, or I could turn it and it would still be the same thing. So that's all really convenient. So what can we get from that? Well, we know that if we flip it this way, we get the same thing. So this triangle and this triangle have to be the same. And then if we, well, since it's a regular hexagon, we know that these are all equilateral triangles, which means that this has to be the same thing. And since this line connects the 2 opposite points in this very symmetric shape, we can also look at some symmetric properties of this shape to get that these triangles have to be the same, which means that this has to be the same as this one, and so on and so forth. You can get this one, and then flip it this way to get this one, this one, this one. It's like kind of like unfolding the square, except we're folding a hexagon. And I'll let you prove it on your own time. There's actually a lot of fast ways to do it, but you do eventually get that all of these triangles are the same area. Maybe figure out how you can fold the paper to show that the most efficiently. That's your exercise. But how does that help us do the problem? Well, now we can start counting. We know that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of these triangles are shaded. And 1, 2, 3, 4, 5, 6. Well, that's 6 in a triangle, and there's 6 triangles. So there should be 6 times 6, which is 36 total. So the answer should be 12 over 36, which is 1/3, which is B. That's not that's not where B is, which is B. And I see that a lot of you are putting B as well. Now, I do see that Albert said that Albert apparently counted wrong, and I think that's a very common mistake. It's very easy to count wrong since 36 is like a relatively big number to count. So maybe you can think about an easier way to do this problem that uses that symmetry I was talking about. Maybe you can look at just one equilateral triangle and see that 2 out of the 6 are shaded. But I'll let you work out the details because it's good exercise. I think that's a pretty pattern, and I'll start working on folding a hexagon snowflake. But while I'm doing that, I think Eli can present the next problem.
Absolutely. You know what all these yellow shaded areas remind me of? First of all, by the way, your answer was right. They remind me of cheese. So, let's do a question about cheese. Matthew the mouse wants to get to a piece of cheese. He can only move horizontally or vertically between 2 cells, and the directions shown in the arrows. So that just means he can go to the right or he can go down. How many different routes can Matthew take to reach a piece of cheese? Okay, I'm going to have a little bit of a bigger diagram here and try to figure this out. And I want to use a method that maybe is not the most direct way to do this, but I think it's really cool, and it's a very general thing that you can use in a lot of different types of questions, which is kind of like working backwards. Because, you know, you could just say, how many ways can I get to this cheese, and like do a calculation that would get you there immediately. And there's probably a clever way to do that. But what I'd rather do is start somewhere simpler. Like, rather than just going to the end immediately, maybe let's go back and think about how we can get to just the second block here. How many different ways we can do that, right? So, I mean, there's only one way to get to this block here, because all that the mouse can do, or is it a mouse? Yeah, it's a mouse, is move, it's Matthew, right? All that Matthew can do is move 1 to the right. And similarly for this one over here, there's also only one way to do that. But then for this next one in the middle, I know you can't see my hand, I'm trying my best. There's actually 2 different ways, because Matthew could either go down from this place where there was one way, or go to the right from this place where there was one way. So there's 2 ways. And the reason that that is because it's like 1 plus 1. We've just added the 2 ways in these 2 other boxes. And now for this next box over here, well, there's only 2 ways to get there, because it just comes straight from the middle box there, because, well, the only way that we can get to this box over here is by moving to the right from the middle box. And similarly for this box here. And now to get to the final cheese down here, if there were 2 ways to get to there, there's going to be 2 ways to get to the final cheese. And then for the middle cheese, well, there's 2 ways to get there and 2 ways to get here. So we just add them together, because for each of the paths that get to there, there's only one way to get to this cheese, and then only one way to get to that cheese from the other direction. So that would be 2 plus 2, which is 4. And then from this one, there's again 2 by a similar reasoning to before. So it's 2 plus 4 plus 2, which is 6 plus 2, or 8. would be our final answer. And this is probably like a little bit overcomplicated for this question. You maybe didn't need to fill out everything, but I think it's really cool. And when you get to like bigger diagrams like this, where it's maybe less clear what's going on, or maybe there's some boxes missing and you have to deal with all of that, it's actually a really useful tool to kind of just start at the beginning and work your way out, like labeling all the numbers and adding things together until you get to the final answer. So just wanted to demonstrate that method. But let's see, that would be option C, and let's see if C is the correct answer. It is. Great job to everyone that said 8 in the chat, and I think we can send it back to Henry.
Wow, I noticed that CC in the chat noticed that the mouse was eating cheese the size of its entire body. Someone should totally take a picture of that. But speaking of pictures, Luis has 3 pictures. One of them seems to be of a clock tower, one of a very nice boat, and then one of what I assume is a squirrel talking to a kangaroo. Or that might be a beaver. But there is a kangaroo. Maybe they're talking about how to eat cheese efficiently. But what we care about is the angles between these 3 pictures. Particularly, we know that this angle is 62, this angle is 42, and we want to find the value of x. So let's start finding angles. They also tell us some useful information that all of our pictures are rectangles. So that means that this is 90 degrees. We know that the angles in a line add up to 180, so the first angle we can find is this orange angle here. So the orange angle is equal to 180 minus 90 minus 62, which is equal to 28. Yep. And then we can try to find x. So the trap here is they want to trick you into thinking it's a triangle, because if you don't look closely, it does look like a triangle. But if you look really, really closely, you'll see that it's actually a concave quadrilateral. Kind of looks like a hang glider. So it's actually this sort of shape. And we know that this angle is 28, this angle is 42, and this big angle, which I'll draw in, what color haven't I used it? I'll draw it in green. This big angle, which is called a reflex angle, is 360 minus 90. So this is actually 270. And we also know that the angles in a quadrilateral add up to 360 degrees, which means that 270 plus 42 plus 28 plus this mystery angle must be equal to 360, which means that 70 plus question mark, I'll just subtract the 270 because it's easy, and then that gives us 70 plus question mark is equal to 90, which tells us that question mark is equal to 20. But 20 doesn't seem to be one of my answer choices. Because it was asking for x, not this angle. So we actually have to do one more step. We know that this angle is 20, and we know that this picture is a rectangle, so this is 90, which means that 90 plus x plus 20 equals a straight line, or 180. And that tells us that x must be equal to 70, which is b. And as CC has noticed, it is b again, which there's been a lot of b's. It's like a hive in here with all the b's. But let's see if we're actually right. And indeed, it was in fact another b. So I guess that means it's time to move on to the next question.
You know, all these bees are making me scared. There's so many bees amassing, and I just want to run away from the bees, but I'm not very good at running, so I'm going to run on a treadmill to practice, okay? Warren is on a treadmill in the gym. He keeps looking at 2 stopwatches. The first shows the time elapsed since he started the session, and the second shows the time remaining until the end of the session. At some point, the two stopwatches show the same reading. What do they show at that point? Okay, if you've ever run on a treadmill before, you may understand what's kind of going on here. And the idea is that, well, when the time remaining is equal to the time elapsed, that's like added together, it's the total time, right? Because each one is like half of the time that's left. Because if I've gone through X minutes and there's X minutes left, that means that the total was 2X. So that means that X itself is half of the total, if that makes any sense. So that's the kind of reasoning that I'm going with. And so when they show the same reading is when they're each half of the total time. So all we have to do now is figure out how much time was there in total for this session. And well, that's not so bad either, because if I've elapsed, well, the first shows time elapsed, yeah. If I've elapsed 14 minutes and 58 seconds, and I have 20, I'm very excited, so I'm having balloons to celebrate my amazing running. And I have 21 minutes and 32 seconds left, and it's just more balloons because every time I do this, there's balloons. So, okay. All I have to do is add these two things together, right? Because that would give us the total amount of time. So 14 plus 21 is like 35, I think. And then we have 32 plus 58. So 2 plus 58 would give me another minute. And then there would be the extra 30 seconds at the end there. So this would be 36 and 30 seconds. So I'll write that as 36:30. And well, now we need to divide it by 2. So, well, whatever half of 36:30 is, and I believe that's just 18:15, right? Because, well, you can just divide each of them by 2. So I believe the answer should be D. I hope, maybe. So I'm going to go with that. And let's see if D is our correct answer. Hey, it is. That's pretty cool. Okay, I think all this exercising has maybe worked up an appetite. So, Henry, do you have a food-related problem for us again?
Yeah, I'm actually getting really hungry, but I don't like having 10 apples, 9 bananas, and 6 pears to eat. So, actually, I'm going to hire a witch to turn my apples into bananas and pears, my bananas into pears and apples, and my pears into apples and bananas. So now I have 15 apples, 7 bananas, and 3 pears. And you can notice by reading the problem closely that every apple has to turn into a banana or a pear. You can't have apples stay apples. So you could do this with a system of 6 equations. So I guess I started writing this out. This is a great idea. And whenever you're doing something hard like writing out a system of 6 equations, you should start thinking, this doesn't seem very fun. Is there an easier way to do this? Some good advice as a mathematician or in anything really is be lazy, or in a nicer way, try to find a slick solution. But I think be lazy works as well. So instead of solving all these equations, let's see if there's a way to do that. Well, I know that every apple has to turn into a banana or a pear. And there's 10 apples, and afterwards, there's 7 bananas and 3 pears, which is 10. Well, what does that mean? Well, that means that the bananas couldn't have contributed anything to the pears, and the pears couldn't have contributed anything to the bananas, which means that the bananas and pears had to all turn into apples, and the apples had to be split into bananas and pears with no other fruits contributing. Wow, that's really nice. So if we were solving a system of 6 equations, a bunch of these would be 0. So the question is asking how many of the apples did she change into bananas? Well, now that we've noticed that, it becomes way easier. We can just look at the number of bananas, since we know that only the apples contributed to the other 2 fruits, to get an answer of 7, which I see a lot of you are putting in the chat, and a lot of you noticed the nice property as well. So let's see if our answer is correct. And indeed, it is 7. So that's a lesson in being lazy or finding slick solutions. But
Yeah.
speaking of slick solutions, I think Eli has a cool problem to talk about.
That was a very magical solution for a very magical type of question. Now it's time for something else that's equally magical, maybe, which is geometry, of course. The side length of the square shown in the diagram is 10 centimeters. Okay, that's cool. The line down in the middle of the square divides it into two equal rectangles. Okay, so this is like dividing it in half, so this is 5 and 5. What is the area of this shaded region in here? Okay, so break out a little bit of a larger diagram so maybe we can figure this out. So I know that this is 5 and 5. I know that this is also 5 and 5, right? Because that's also splitting it down the middle. These are diagonals. And now I just have to find the area of this triangle and this triangle and then add them together, and that would be the area of the shaded region. So actually this isn't that bad because it may look a little strange, but this is just a triangle and we kind of know its base and height, right? This is its base, this side length of 5 here. That's the base of our triangle. And the height of the triangle, it looks weird because the height is so far from the actual triangle, but its height is also just 5. I mean, imagine that the height is here. This is the perpendicular that you drop from this vertex point to this side. That is literally just the height. So this is 5 for the height. And so that means this is 5 times 5 over 2, but there's two of them. So it's just 5 times 5, which is 25. And that would be the area of this shaded region here. Okay, which option is that? That looks like option B. So is B our correct answer, as many people are saying in there? And yes, it's yet another B. It is yet another B. But maybe, Henry, will the next one also be B? Please don't let it be B.
I sure hope it's not a B. This scare me. One of them stung me once and it hurt. But we do have some more geometry. As far as I know, geometry has never stung me, so I'm a fan of that. We have a quadrilateral A, B, C, D, and we have points N and K such that BN is 2NC and AK is KD. So I'll mark that on here. AK is equal to KD and BN is equal to 2NC. And we also know that the area of triangle CKD is 2 and the area of triangle ABN is equal to 6. And we want to find the area of the whole quadrilateral. So we're just missing this inner bit. Unfortunately, I don't know the formula to find the area of this shape. So whenever you're hit with this type of conundrum, something you should always try is to split it into things that you do know how to do. And something that I know how to find the area of is triangles. So let's split this shape into two triangles. But they didn't give me any side lengths. They only gave me the areas of other triangles. So it would be really convenient if we could get the area of these triangles from the areas of the other triangles. Well, let's look at ACK. We know the base, it's the same as KD. So now we just need the height. But the height is the distance from C to AD, which means that the base and the height of AKC is the same as the base and height of KDC, which means that AKC also has area 2. And then we can do the same thing. The height of ANC is the distance from A to line BC, so the height is the same, and we know that the base is half of BN. So ANC has to have area half of ABN, which is equal to 3. So now we can just add them up. We get 6 plus 3 plus 2 plus 2, which is equal to 13, which is answer choice A, which very luckily is not answer choice B. So keep in mind this base and height argument for finding the areas of things based on the areas of other shapes, because that's a pretty common tool to use. And it's very neat to notice this in a problem that asks you for the area of something that seems like you wouldn't be able to find the area of. But let's see if our answer is actually correct. And indeed, the answer is 13. So I think it's time to move on to the next problem.
Yeah, awesome job, Henry, escaping from those bees. And as our prize for escaping for the bees, we're going to get some pearls. But oh no, we don't know how to find the pearls that we want. Okay, Adira keeps golden, red, black, pink, and white pearls in 5 small boxes. Each box contains pearls of only one color. The boxes are labeled like this, and all the labels are actually true. So if it says golden or red, it either has golden or red. Adira's friend Lily wants to know which box contains the golden pearls. She may open exactly one of the 5 boxes to look inside. Which box must Lily open to be certain which of the boxes contains the golden pearls? And this is, like, I think, a really tricky question because it's not asking which box actually has the golden pearls. It's asking which one should you open to know which of the 5 has the golden pearls. So obviously, if you open the one that has the golden pearls, you'll know that. But you might have to open one that's actually not the golden pearl box to know which one does have the golden pearls. So let's make this a little bit bigger, see what we're working with. And okay, the total, I think we just have to label them like G. Okay, so let's see what our colors are. It's golden, red, pink, black, and white. Are those the colors? I think so. So the first box is golden or red. This one is not black. I'm just going to use my fancy logic notation because it's fun. This one's pink or black. This one's pink or white. Okay. And this one's black or golden. A lot of people saying maybe option C, but let's see if we can see why that is, or see why it isn't. Well, there's only 2 boxes that actually have golden in them, right? Or this one could also have it, right? This is not black. But these 2 definitely don't have anything golden in them because it's just pink or black and pink or white. So I don't know if those would actually tell us any pertinent information. Maybe they would. But the 3 possibilities for which one has the golden one are these 3 here, right? This one is either black or golden, this one's not black, and this one's golden or red. So let's just kind of go through some scenarios and see if we can figure out, like, if they actually give us any information. So for the last one here, black or golden, if I open that and I get something that's golden, then I'll be done. So let's say I get something that's black. Well, I mean, that doesn't really tell me anything because none of the other ones even say anything about black except for this one, which is not black. And that certainly doesn't tell me anything else. This being black doesn't tell me anything about this being not black because that's certainly true anyway. So I feel like this just doesn't give me any information. It's probably not this one. Maybe it is. We can come back to it. But it's not giving me the right vibe. Okay, pink or white. For this one, if I open it and it's pink, that would mean this one's black, right? Because this is pink or black. But I don't think that really tells me anything about the golden or red. Well, actually, I have to see. Does each boxes contains pearls of only one color, and all the pearls are contained in all the boxes, right? Golden, red, black, pink, and white. Okay, so yeah, there's 5 boxes. I imagine each one contains exactly one, and all 5 are there. I think that's what this is saying. So actually, if that's true, I'm realizing that the only one that could have red. Oh, actually, both of these could. Because this one says golden or red. These 3 don't mention anything red. This one says not black. So the only ones that could actually have red in them are these 2. Maybe that's something that's useful. I don't know. But if this has pink, then that would mean this has black. And I think you still can't necessarily figure out which one is which here. Yeah. Oh, wait, no, it would. If this is pink, then this one is black. And so this one can't be black, which means it's golden. So actually, if this is pink, then you do have your answer. Okay, what if this is white? If this is white, then I don't think you get any information. So I'm still thinking it's not this one. Okay, I'm gonna X that one out. Go on to the next one. Go on to C, which is what a lot of people are saying. Pink or black here. Okay, if this is pink, then this one can't be pink, so it's white. So this is pink and white. And do we know anything else? Well, I mean, pink, white, and one of these could still be red. I mean, this could be red, golden, and black, or it could be red, golden, and black. So I think you can't actually tell in that case either. So I don't know. Oh, that wasn't C. This was C. Oh, but everyone was saying that this is the answer. Well, we can come back to it. I still don't think this is the answer, so I'm going to X that one out. Not black. If I open that one and I get something, I mean, I don't know. There's a lot of different options for what that is, so my guess is that isn't the answer either. And now I think I'm just going to X out every single one of my answer choices, which isn't very good. And now golden or red. If I open that and it's red, that tells me literally nothing because red isn't mentioned anywhere, and if it's golden, obviously, that tells me the answer. So, okay, I think I have to go back and get rid of some of my X's. I think we have to go back to the first one here that I looked at, which was C. Black or golden? If it's golden, then we're done. If it's black, then this one has to be pink, which means this one's white. Okay, I think that's what I missed before. If this is black, then that means this one's got to be pink, so this one is white. And now, I still think, like, couldn't this one be red and this one golden? Or this one golden and this one red? I think, yeah, that could happen. So I don't think this would actually tell us the answer. So I think everyone in the chat was saying C, so but I don't think that's right. So I'm gonna go back to Xing this out. And I know it's 8. This is the last question. We're almost done, maybe, hopefully. I don't know. Maybe Henry would want to help me out if I can't figure this out. So, pink or white? Okay, if it's pink. If it's pink, then this is black, and this is golden. So that tells me the answer. If this is white, then what do I get from that? I don't know. If this is white, I feel like I don't get any information. Let's see. Everyone's saying now that it's D. Some people are saying that it's D. But really? Not black? Could that possibly give me anything? If it's not black, like if it's golden, then I'm done. If it's red, then this is golden. Okay. If it's pink, then this one's black, which means this one's golden. Okay. If it's black, it can't be. If it's white, then this is pink. Then this is black. Then that's golden. Oh my God. It actually just is this one. That is so crazy. That is such a cool question. It's just this answer because, okay, this, if you go through each of the possibilities, if it's golden, then you're done. You know that it's this one. If it's red, then this one's got to be golden because this is golden or red. If it's pink, then this one's got to be black because it's pink or black, which means this one is golden because this is black or golden. And if it's black, it can't be black, so we just move on. If it's white, then this one's pink, which means this one's black, which means this one's golden. So it's actually this test. That is the actually coolest thing I've ever seen. That's so cool. Okay, but I think the answer would actually be D. Let's see. It is. Wow, so cool. Okay, I think that's the end of our live solve. Maybe we can get Henry back here with me.
I do want to mention, really quickly, there's like a bit of a cheese way to do this last one as well. You can, if you want to cheese it, you can notice that the golden one can be in like at least 3 different chests and it still works. And each of the other 4 would only give you 2 options. So the only one that gives you more than 2 options is not black. So that's the only one that has a possibility of dividing between 3 different options. So that's a cheese way to do it, but it's not rigorous. So Eli's way is the rigorous way to see why not black works.
Okay, well, I think that's the end of our live solve for today. Thank you, everyone, for coming. And, yeah, I guess we'll end it here. So, bye, everyone.
Yeah, thank you all for coming. This was quite fun. These are some very, very nice problems.
Especially this one.
Especially that
That's
last
cool.
one, yeah.